Bayesian inference is a method of statistical inference in which Baeza theorem is used to update the probability for a hypothesis as evidence. Bayesian inference is an important technique in statistics, and especially in mathematical statistics. Bayesian updating is particularly important in the dynamic analysis of a sequence of data. Bayesian inference has found application in a wide range of activities, including science, engineering, philosophy, medicine, sport, and law. In the philosophy of decision theory, Bayesian inference is closely related to subjective probability, often called Bayesian probability. Introduction to Baeza rule. Formal Bayesian inference derives the posterior probability as a consequence of two antecedents: a prior probability and likelihood function, derived from a statistical model for the observed data. Bayesian inference computes the posterior probability according to Baeza theorem, where denotes a conditional probability. More specifically, it means given stands for any hypothesis whose probability may be affected by data. Often there are competing hypotheses, from which one chooses the most probable. The evidence corresponds to new data that were not used in computing the prior probability. The prior probability is the probability of before is observed. This indicates one's previous estimate of the probability that a hypothesis is true, before gaining the current evidence. The posterior probability is the probability of given, i.e., after is observed. This tells us what we want to know. The probability of a hypothesis given the observed evidence is the probability of observing given. As a function of with fixed, this is the likelihood. The likelihood function should not be confused with as a function of rather than of. It indicates the compatibility of the evidence with the given hypothesis. Is sometimes termed the marginal likelihood or model evidence. This factor is the same for all possible hypotheses being considered. This means that this factor does not enter into determining the relative probabilities of different hypotheses. Note that, for different values of only the factors and affect the value of, as both of these factors appear in the numerator, the posterior probability is proportional to both. In words, the posterior probability of a hypothesis is determined by a combination of the inherent likeliness of a hypothesis and the compatibility of the observed evidence with the hypothesis. Posterior is proportional to likelihood times prior. Note that Baeza rule can also be written as follows, where the factor represents the impact of on the probability of. Informal: if the evidence does not match up with the hypothesis, one should reject the hypothesis. But if a hypothesis is extremely unlikely a priori, one should also reject it, even if the evidence does appear to match up. For example, imagine that I have various hypotheses about the nature of a newborn baby of a friend, including: the baby is a brown-haired boy, the baby is a blonde-haired girl, the baby is a dog. Then consider two scenarios. I'm presented with evidence in the form of a picture of a blonde-haired baby girl. I find this evidence supports and opposes an. I'm presented with evidence in the form of a picture of a baby dog. Although this evidence, treated in isolation, supports my prior belief in this hypothesis is extremely small, so the posterior probability is nevertheless small. The critical point about Bayesian inference, then, is that it provides a principled way of combining new evidence with prior beliefs through the application of Baeza rule. Furthermore, Baeza rule can be applied iteratively. After observing some evidence, the resulting posterior probability can then be treated as a prior probability, and a new posterior probability computed from new evidence. This allows for Bayesian principles to be applied to various kinds of evidence, whether viewed all at once or over time. This procedure is termed Bayesian updating. Alternatives to Bayesian updating: Bayesian updating is widely used and computationally convenient. However, it is not the only updating rule that might be considered rational. Ian Hacking noted that traditional Dutch book arguments did not specify Bayesian updating. They left open the possibility that non-Bayesian updating rules could avoid Dutch books. Hacking wrote, and neither the Dutch book Argument, nor any other in the personalist arsenal of proofs of the probability axioms, entails the dynamic assumption. Not one entails Bayesianism. So the personalist requires the dynamic assumption to be Bayesian. It is true that in consistency a personalist could abandon the Bayesian model of learning from experience. Salt could lose its savor. Indeed, there are non-Bayesian updating rules that also avoid Dutch books before any data is observed, i.e., the prior distribution might not be easily determined. In this case, we can use the Jeffreys prior to obtain the posterior distribution before updating them with newer observations. The sampling distribution is the distribution of the observed data conditional on its parameters, i.e., this is also termed the likelihood, especially when viewed as a function of the parameter, sometimes written. The marginal likelihood is the distribution of the observed data marginalized over the parameter, i.e., the posterior distribution is the distribution of the parameter after taking into account the observed data. This is determined by Bayes' rule, which forms the heart of Bayesian inference. Note that this is expressed in words as posterior is proportional to likelihood times prior, or sometimes as posterior equals likelihood times prior, over evidence. Bayesian prediction. The posterior predictive distribution is the distribution of a new data point, marginalized over the posterior. The prior predictive distribution is the distribution of a new data point, marginalized over the prior. Bayesian theory calls for the use of the posterior predictive distribution to do predictive inference, i.e., to predict the distribution of a new, unobserved data point. That is, instead of a fixed point as a prediction, a distribution over possible points is returned. Only this way is the entire posterior distribution of the parameter used. By comparison, prediction in frequentist statistics often involves finding an optimum point estimate of the parameter, e.g., by maximum likelihood or maximum a posteriori estimation, and then plugging this estimate into the formula for the distribution of a data point. This has the disadvantage that it does not account for any uncertainty in the value of the parameter, and hence will underestimate the variance of the predictive distribution. The average of normally distributed random variables is also normally distributed, the predictive distribution of a normally distributed data point, with unknown mean and variance. Using conjugate or uninformative priors, has a student's t-distribution. In Bayesian statistics, however, the posterior predictive distribution can always be determined exactly, or at least, to an arbitrary level of precision. When numerical methods are used, note that both types of predictive distributions have the form of a compound probability distribution. In fact, if the prior distribution is a conjugate prior, and hence the prior and posterior distributions come from the same family, it can easily be seen that both prior and posterior predictive distributions also come from the same family of compound distributions. The only difference is that the posterior predictive distribution uses the updated values of the hyperparameters, while the prior predictive distribution uses the values of the hyperparameters that appear in the prior distribution. Inference over exclusive and exhaustive possibilities. If evidence is simultaneously used to update belief over a set of exclusive and exhaustive propositions, Bayesian inference may be thought of as acting on this belief distribution as a whole. General formulation. Suppose a process is generating independent and identically distributed events, but the probability distribution is unknown. Let the event space represent the current state of belief for this process. Each model is represented by event. The conditional probabilities are specified to define the models. Is the degree of belief in, before the first inference step, is a set of initial prior probabilities. These must sum to 1, but are otherwise arbitrary. Suppose that the process is observed to generate. For each, the prior is updated to the posterior. From Baeza Theorem. Upon observation of further evidence, this procedure may be repeated. Multiple observations for a sequence of independent and identically distributed observations. It can be shown by induction that repeated application of the above is equivalent to where parametric formulation by parameterizing the space of models. The belief in all models may be updated in a single step. The distribution of belief over the model space may then be thought of as a distribution of belief over the parameter space. The distributions in this section are expressed as continuous, represented by probability densities, as this is the usual situation. The technique is however equally applicable to discrete distributions. Let the vector span the parameter space. Let the initial prior distribution over B, where is a set of parameters to the prior itself, or hyperparameters. Let be a sequence of independent and identically distributed event observations, where all are distributed as for some. Baeza theorem is applied to find the posterior distribution over, where mathematical properties, interpretation of factor, that is, if the model were true, the evidence would be more likely than is predicted by the current state of belief. The reverse applies for a decrease in belief. If the belief does not change, that is, the evidence is independent of the model. If the model were true, the evidence would be exactly as likely as predicted by the current state of belief. Cromwell's rule if-then. This can be interpreted to mean that hard convictions are insensitive to counter-evidence. The former follows directly from Baeza theorem. The latter can be derived by applying the first rule to the event, not, in place of, yielding, if-then, from which the result immediately follows. Asymptotic behavior of posterior. Consider the behavior of a belief distribution as it is updated a large number of times with independent and identically distributed trials. For sufficiently nice prior probabilities, the Bernstein-von Mises theorem gives that in the limit of infinite trials, the posterior converges to a Gaussian distribution independent of the initial prior under some conditions firstly outlined and rigorously proven by Joseph L. Dubin 1948, namely if the random variable in consideration has a finite probability space. The more general results were obtained later by the statistician David A. Friedman, who published in two seminal research papers in 1963 and 1965 when and under what circumstances the asymptotic behavior of posterior is guaranteed. His 1963 paper treats, like Dubin, the finite case and comes to a satisfactory conclusion. However, if the random variable has an infinite but countable probability space, the 1965 paper demonstrates that for a dense subset of priors, the Bernstein-von Mises theorem is not applicable. In this case there is almost surely no asymptotic convergence. Later in the 1980s and 1990s, Friedman and Percy Diaconis continued to work on the case of infinite countable probability spaces. To summarize, there may be insufficient trials to suppress the effects of the initial choice, and especially for large systems the convergence might be very slow. Conjugate priors in parameterized form. The prior distribution is often assumed to come from a family of distributions called conjugate priors. The usefulness of a conjugate prior is that the corresponding posterior distribution will be in the same family, and the calculation may be expressed in closed form. Estimates of parameters and predictions. It is often desired to use a posterior distribution to estimate a parameter or variable. Several methods of Bayesian estimation select measurements of central tendency from the posterior distribution. For one-dimensional problems, a unique median exists. For practical continuous problems, the posterior median is attractive as a robust estimator. If there exists a finite mean for the posterior distribution, then the posterior mean is a method of estimation. Taking a value with the greatest probability defines maximum a posteriori estimates. There are examples where no maximum is attained, in which case the set of map estimates is empty. There are other methods of estimation that minimize the posterior risk with respect to a loss function, and these are of interest to statistical decision theory using the sampling distribution. The posterior predictive distribution of a new observation is determined by examples. Probability of a hypothesis. Suppose there are 2 full bowls of cookies. Bowl number 1 has 10 chocolate chip and 30 plain cookies, while bowl number 2 has 20 of each. Our friend Fred picks a bowl at random, and then picks a cookie at random. We may assume there is no reason to believe Fred treats one bowl differently from another. Likewise for the cookies. The cookie turns out to be a plain one. How probable is it that Fred picked it out of bowl number 1? Intuitively, it seems clear that the answer should be more than a half, since there are more plain cookies in bowl number 1. The precise answer is given by Baeza Theorem. Let correspond to bowl number 1, and to bowl number 2. It is given that the bowls are identical from Fred's point of view, thus, and the 2 must add up to 1, so both are equal to 0.5. The event is the observation of a plain cookie. From the contents of the bowls, we know that an Baeza formula then yields before we observed the cookie. The probability we assigned for Fred having chosen bowl number 1 was the prior probability, which was 0.5. After observing the cookie, we must revise the probability to, which is 0.6. Making a prediction. An archaeologist is working at a site thought to be from the medieval period, between the 11th century to the 16th century. However, it is uncertain exactly when in this period the site was inhabited. Fragments of pottery are found, some of which are glazed and some of which are decorated. It is expected that if the site were inhabited during the early medieval period, then 1% of the pottery would be glazed and 50% of its area decorated. Whereas if it had been inhabited in the late medieval period, then 81% would be glazed and 5% of its area decorated. How confident can the archaeologist be in the date of inhabitation as fragments are unearthed? The degree of belief in the continuous variable is to be calculated, with the discrete set of events as evidence, assuming linear variation of glaze and decoration with time, and that these variables are independent. These numbers don't appear to match the numbers in the description above. If they do, more explanation is needed. For example, where are 81% and 5% incorporated? Assume a uniform prior of, and that trials are independent and identically distributed. When a new fragment of type is discovered, Baeza theorem is applied to update the degree of belief for each. A computer simulation of the changing belief as 50 fragments are unearthed is shown on the graph. In the simulation, the site was inhabited around 1420, or by calculating the area under the relevant portion of the graph for 50 trials. The archaeologist can say that there is practically no chance the site was inhabited in the 11th and 12th centuries. About 1% chance that it was inhabited during the 13th century, 63% chance during the 14th century and 36% during the 15th century. Note that the Bernstein von Mises theorem asserts here the asymptotic convergence to the through distribution because the probability space corresponding to the discrete set of events is finite.